Okay, so we're going to continue on where we left off last lecture. This will be lecture number 3, part 5, I believe. Lecture number 3, part 5. And we're going to continue with implicit differentiation. And so we had one, the last problem we worked was the derivative of the inverse secant function. We calculated the derivative of the inverse secant function. So now today we're going to calculate the derivative of the inverse cosecant function. So let's see what it looks like. So you know that the cosecant function is 1 over sine x. It's the reciprocal of the sine function. And so its graph will, let's see if we can pull up a picture of its graph. Make sure. Right. So let me type. So, as before, we need to identify the principal part of the cosecant function so that we can get the one-to-one component so that we can work with an inverse. So if we explore the graph, y is equal to what? CSC of x, and that will be shown in red. So let me set my window properties. Window settings, we want the x-axis labels to be in terms of pi, and so here we have the cosecant function is shown in red. All right, so now it appears that an appropriate principal part of the cosecant function would be, say, this branch. If we start at this point, and would be this branch. Okay, so if we peel off these parts of the cosecant function, we'll have the principal, which is uppercase C, CSC. Y is equal to cosecant x. All right, and so the domain of the principal part would be negative pi halves to 0, exclusive union 0 to pi halves. So this will be the domain of the principal part. And then your range, you can see it ranges from, the range would be what? Negative infinity, oops, I need to open the brace, right? Negative infinity up to -1, union 1, well, we include 1 because 1 is in the range, so it would be union 1 to infinity. Okay, so this is the attributed principal cosecant x. All right, and now so let's see here. One other thing we probably should graph on here would be the cotangent function, because we'll be needing that when we do the implicit differentiation, and that'll be shown in blue. So the cotangent function, the remarks I want to make about cotangent is on the domain of the principal cosecant function, we see that from negative pi halves to 0, the cotangent function is less than 0. And from 0 to pi halves, the cotangent function is greater than 0. So we'll need those facts when we calculate the derivative of the inverse cosecant function. So as before, we say y is equal to inverse cosecant of x, or arc cosecant of x. I'll write inverse cosecant of x just for just to make things clear. So inverse cosecant of x. Then we take the principal cosecant of both sides of the equation. So we'll have principal cosecant of y is equal to x. And then we'll use implicit differentiation. So we know that the derivative of the cosecant function is minus cosecant y cotangent y is equal to times dy over dx. I have to use the chain rule. Don't forget the chain rule is equal to 1. And so when we solve for dy over dx, we have dy over dx is equal to -1 divided by cosecant y cotangent y. Okay, and so we know if x is equal to we need to replace cotangent y with its expression in x. So we know, how do we do that? So we know that sine squared y, from trigonometry, we have sine squared y plus cosine squared y is equal to 1. Now if I divide both sides of this equation by sine squared y, I'll have 1 plus cotangent squared y is equal to cosecant squared y. Okay, so that's an important trig identity. And then we can solve for cotangent squared y. So cotangent squared y is equal to cosecant squared y minus 1, and then solve for cotangent y. So cotangent y is equal to plus or minus the square root of cosecant squared y minus 1. So if you recall from the graph, the cosecant function, or the principal cosecant function on, let's see, on, so we have basically we're going to have a piecewise defined situation that we have to take care of. So if we consider the interval -π² to 0. So let's consider this interval for the for cosecant y and cotangent y. So on this interval, cosecant y is less than 0, and we deduce that from the graph. Okay. Also on this interval, cotangent y is less than 0. Okay. So we have this piece of information. So the product of cosecant y times cotangent y, this product on this interval will be greater than 0 because the product of two negative quantities is positive. All right, so that means now all we have to do is replace this expression, this whole expression, rewrite it in terms of x. Okay, so all right, so let's do that. So we have dy over dx, the derivative of y with respect to x, would equal to -1. Now the cosecant of y is right here, is equal to x. All right, so that would be x. And, well, we can just replace cotangent of y with this. And so that would be cosecant squared of y minus 1. And since both quantities are negative, okay, so if we look at the interval from -π² to 0, okay, so now let's consider this interval. If x were greater than, we know for the inverse cosecant function that the domain of the inverse cosecant function, well, we should really take a look at that, right? So that's missing on this graph. So let's take a look at the arc cosecant function, what its graph looks like, because we need to understand its domain. We need to understand the arc cosecant function domain. So y is equal to arc cosecant x. Okay, and if we look at the graph shown in red, Let me adjust my window again. So if we look at the graph, the domain of the arc cosecant function, which is shown here in red, is what? X is greater than 1 or X is less than -1. So let me write the domain. Well, on the next slide. Okay, so take a good look at this. Because we'll need that in our calculations for the derivative. So when we calculate the derivative of the arc cosecant function, we have to conform to where the arc cosecant function exists. So what I'm going to write here is note based on the graph that we just saw, the domain of the inverse cosecant function x is equal to this. So there's an important calculus lesson here. -infinity up to -1 inclusive, union 1 to infinity. So this is the domain of the arc cosecant function. And so this also happens to be the domain of the derivative of the arc cosecant function. Okay? The derivatives of functions share the same domains as their functions. Okay? So this is also equal to, so that's an important fact that I don't think the textbook mentions. Okay? So we have to adhere to this concept. Okay, because we can't create tangential lines to this graph between -1 and 1 because there's nothing to structure a tangential line with. There's no content there. So that being the case, if we were to choose a value for x, say on this part of the domain, okay, then x is less than 0. Okay, and what would happen is if we plugged in a negative number in for x, then our derivative would be positive. Do you see that? Say like if I plugged in -4 for x, I would have a positive quantity. So, but look what happens. Just look at the graph alone. Let's go back and well, let's see. Let me put a static image one that doesn't change all the time. So let's look at the graph of the inverse cosecant function again. I'm going to paste it here. So here it is. Spin the page some more. Now, if x were -4, okay, so let's identify -4. So or choose some x that's where we see the graph. So say x were -π½ right here. The tangential line at -π½ would look something like this, right? That would be a representation of a tangential line at π², just eyeballing it. And you can readily tell that the slope of this tangential line is negative because lines that are pointing in this direction, oriented this way, have negative slopes. So just looking at the graph, proof through pictures, if we plug in a negative number, we have to have a negative slope, which is what this derivative is. So again, we're emphasizing what the meaning of dy over dx is. It's the slope of the tangent line to a particular value of x, to the function. So we have to make an adjustment to this formula for the derivative. We have to use absolute value so that the negative values of x won't cancel the effect of the -1 and produce a positive output. Right? So that's why we use absolute value to account for negative numbers, because this is the domain for the derivative of the inverse secant function. And then we're okay here. Okay, so for positive numbers, well, the absolute value of a positive number is just a number itself, so we can just leave the absolute value in and still. And if you note the graph again, Okay, again, so if you're on this side for x greater than whatever this is, x greater than 1, okay, again, you'll see the appearance of the slopes of the tangential lines all have negative slopes. Okay, so that's why we have to induce the absolute value bars here. All right, so I hope this makes sense. There's a lot of work that goes into the calculations of the inverse secant and inverse cosecant functions, and I'm hoping you follow that. So if you have any questions, get with me and we can talk about it. All right, so let's do some problems, some more problems. How about we do, let's see, from the text, question number 68. So let me see what that is. I had that one flagged for some, I'm pulling up the text right now, looking at the book. Section 3.5, number 68. Okay, so is that the one I wanted to deal with? Or is it 67? Maybe I'm looking at a different book here. Hang on. Let's see, there was a problem here. Oh, okay, I beg your pardon. This will actually be, let's see here. Trying to find where the problem is in the book. Okay, so let's do problem number 77 on page 217 of the 7th edition of the Stewart book. All right, so we have f. So let's see here. Let's write it up this way. So suppose f, some function f, is 1-to-1 and is differentiable. Okay, so is differentiable. All right, and let's see what else I have. Its inverse function, okay, f inverse is also differentiable. All right, so we're given this information. Okay, and so what we want to do is we want to calculate the derivative of the inverse function. So find this. Now remember, this -1 means the inverse, not the reciprocal. It's the difference. So we want to calculate the derivative of the inverse of the function. Okay, so how do we do that? So we say, okay, well, what I would propose is we say let y equal to f of x. So f of x is a continuous 1-to-1 differentiable function. And so take the inverse of both sides. So we have f of y. I'm sorry, hold up. Let y equal f inverse of x, like that. Okay, let's let y equal f inverse of x. So we want to find y prime. So WTF, want to find y prime. Okay, so fy, the function of y, is equal to x. All right, like that. Okay, so now if we differentiate both sides, we have f prime of y, and then we have to use the chain rule. dy over dx, the derivative of y with respect to x by the chain rule, is equal to 1. Okay, and so now we have derivative of y with respect to x is equal to 1 over f prime of y. Okay, and then we just plug in our value for y. But y is equal to what? Y is equal to f inverse of x, right? So we have dy over dx is equal to 1 divided by f prime of f inverse of x. Okay, so, and this is a very, very important theorem in mathematics. Okay, so it deals with a branch of mathematics called chaos theory. Okay, so if I ask you, let's see here, what kind of questions can we ask here? Let's see. Okay, I think we can leave it at that. Okay, let's see here. Well, okay, yeah, so here's a kind of question that looks interesting. Suppose I give you this function. F of x is equal to 2x plus cosine x. Okay, show f of x is 1 to 1. Okay, this is an aside. All right, so, well, how can we show a function is 1 to 1? So we actually have a new technique of showing functions being 1 to 1. We can take the derivative of f of x. This is a different problem now. Okay, the derivative of f is 2 plus sine x. Okay, and this function is greater than 0 for all x, right? Because the smallest value the sine function can take on is -1, and 2 minus 1 is 1. So no matter what x you give to f prime of x, it's always greater than 0. So what does this mean? This means that what? F is an increasing function for all x. And how do we know it's an increasing function? Because the slopes of the tangent lines are always positive. Okay, and if you remember, if you have a function, okay, that always has positive slopes for tangent lines, then it has to be an increasing function. If the derivative of a function is always greater than 0, then the function itself is an increasing function. All right, so we have an increasing function. So what does that mean? Increasing functions are 1 to 1 on their intervals for which they're increasing. Okay, so that's a takeaway. So note, since f is an increasing function for all x, f has to be 1 to 1. Okay, so a very important fact, a very important geometric fact. Okay, so let's see here. Can we find, so the question is, can we find f inverse of 1? What is that equal to? Okay, well, do you want to sit here and calculate the inverse of this function? I certainly should hope not. That would be very complicated indeed. So how do we calculate this? So one way we can deal with it is, well, we know, let's let f inverse of 1 equal to some number k, all right? So that means, since we know that the function is essentially 1 to 1, we can say that f of k is equal to 1. Okay? So all we have to do then is we have to solve 2k plus what is the function? Cosine 2k plus cosine k. Where does that equal to 1? Okay, well, by inspection, what if k is equal to 0? If k is equal to 0, then we would have 0 plus cosine of 0 is equal to 1, and that holds. So just by inspection alone, k is equal to 0. And so therefore we would have f inverse of 1 must equal to 0. Okay, so that was kind of a trick question there. All right. Uh, next question I want to deal with, is this the last question of the topic? Oh, we got a couple more. Okay. So I want to do a word problem. So let me pull it from the book. This would be number 80, question number 80 on page 217 of the text. So I have the drawing here. I'll paste the drawing in. So bear with me while I collect it. I'm pasting the drawing for the figure for problem 80 into the whiteboard session. So let me touch it up a bit. So let me delete some of this writing here. All right, let me select the drawing. Okay, let me pull up whiteboard again. Okay, and let's go to a new page. So here we have the illustration used from the text. All right, so what we have here is we have a lamp, which I'll accentuate, say, in purple right here. So we have this lamp, okay, and it's located 3 units to the right of the y-axis. So we have this distance right here as being 3. So there's your 3 units. Okay, so it's 3 units to the right of a y-axis. And what's happening is the light beam from the lamp, it shines down on the ground, and we have this elliptical region as shown here. So I'll accentuate. So we've got this elliptical region right here. Okay, so there's an elliptical region. And what happens is, okay, and so, yeah, so the elliptical region is the region defined by the boundary x squared plus 4y squared is equal to 5. All right, so that's the equation of that ellipse. And so it's kind of like an obstruction. And what happens is the shadow cast is in this hashed area right here. So it casts a shadow right here in this region as the light shines down. Okay, so we've got this shadowy region like thus. Okay, and let's see. And so right here, we've got a ground. Okay, this is the ground reference layer. And so this would be the extent of the shadow. So right here. So the shadow is all of this region right here. Okay. So this wherever I have the green, that's the shadowy area. So we want to know essentially the height of the lamp. Okay. So the height of the lamp, h, which I've got delineated as here, h. Okay. So we've taken these measurements. We've got this elliptical object that blocks the light beam and casts a shadow in this configuration with respect to the ground. And so how high is the lamp? Okay, so here's how we can solve it. It's an implicit differentiation problem. So we have the equation of the ellipse, which is x squared plus 4y squared is equal to 5. Okay? Now, so if we were to use implicit differentiation, we would have 2x plus 8y y prime is equal to 0. So why do we want to take the derivative? What does that help us with? Well, let's just hold on. Let's see here what that can help us with. So we have h is the height of the lamp. Okay, and what else do we have? Okay, so we have this point right here that I've delineated as AB. So the point AB, okay, is a point of tangency passing through which points? So we have 2 points, right? Okay, so it's a point of tangency of the line, of the line. Passing through 2 points that you see on the illustration. Passing through (3h), which is the coordinates of the height of the lamp, and -5, 0. Okay, so AB is the point of tangency on the ellipse of the line connecting these 2 points. So what is the slope of this tangent line? Well, M is equal to what? H minus 0 divided by 3 minus 5. Okay, which is equal to H8, H over 8. Okay, and we're trying to solve for H. But we're also given the fact that we know that so this is the slope of the tangent line to the ellipse. But we also know that the slope of any tangent line to the ellipse may be found this way, by taking the derivative with respect to x of the equation of the ellipse. So if we solve for y prime, we'll get another equation for the ellipse in terms of x and y. So y prime, which is equal to the slope of the tangent line, is equal to what? Negative 2x over 8y, which is equal to what? Negative x over 4y. Okay, and so and this happens in particular at AB. So if xy is equal to AB, we can plug in at the point of tangency AB, the slope of the tangent line at the point of tangency AB would be negative a over 4b. Okay, and this also happens to equal to b minus 0 over a minus 5, right? Because these 2 points right here are on the tangent line, and so we can calculate the slope of the tangent line based on these 2 points, and we can calculate the slope of the tangent line based on taking the derivative of the equation for the ellipse. Okay, so now we can cross multiply. So cross multiply and we can solve for A in terms of B or vice versa. Okay, so if we cross multiply, a technique from algebra, we'll get what? 4b squared is equal to minus a squared minus 5a. Okay, and then so we have that expression. All right, so what else do we have? Okay. We also have what? We also have the equation. We also know that a squared plus 4b squared is equal to 5. How do we know that? Because we have the equation right here. We plug in a and b. Okay, so that holds true. Okay, so let's see what else we can do here. Okay, so we can replace b squared, 4b squared with 5 minus a squared. We can try that. What else can we try? 4b squared is equal to, okay, so let's see here. Okay, so if we were to, we have two equations now, so let's see here. We have yeah, so we have two equations. So if we call this equation 1, we call this equation 2, we have, let's see here, we have a squared plus 4b squared is equal to minus 5a. And then we have a squared plus 4b squared is equal to 5. Okay? And so that means that 5 is equal to minus 5a. And so that means that a has to be negative 1. And b has to be what? 1. So we'll take b equals to 1. Why does b equal to 1 and not negative 1? Because if we look at the position of AB, it's in quadrant 2, and all ordinates in quadrant 2 are positive. So we have values for A and B. And so now we go back to our equation for H. Somewhere around here we had an equation for H. Yes, we had H over 8 is also the slope of the tangent line. So we have H over 8 must equal to the slope of the tangent line, which we said was B over a plus 5. Okay, that came from here, this equation. And so now we can solve for h. So we have h over 8 is equal to 1 over 4. So h is equal to 2 meters, or what is it? I guess feet or meters, whatever the dimensions were. So we'll say h is equal to 2 meters. Okay. So nifty little technique for finding the height of a lamppost. Just take an ellipse and stick it on the ground in its proximity, measure the shadow, and you can find it using calculus. All right. Okay, so let's do another problem. Let's calculate the derivative of a composite function using that has inverse components to it. Okay, so how about, I'm not sure if this is in the text or not. How about we calculate the derivative of this function with respect to x? Y is equal to arctan of the square root of what? 1 minus x over 1 plus x. Okay, so what is y prime? Okay, well, recall that the derivative of the arctan, okay, so, well, okay, we have, let's let u equal to the argument. Or can we do better? How about we simplify it even further? Let's let u, how about we let u equal to 1 minus x over 1 plus x. Okay, 1 plus x. And how about we let v equal to the square root of u? Okay, and so what we want is we want the arctan, so y is equal to the arctan of v. Okay, so the derivative of y with respect to x would equal to the derivative of arctan. Well, let's see, not yet. Don't write it just yet. Let's see. That would equal to the derivative of y with respect to v times the derivative of v with respect to u, okay, times the derivative of u with respect to x. Okay, so that would be what we're chasing here. So we know that the derivative of y with respect to v is just the derivative of the arctan function, which is 1 over 1 plus v squared. And the derivative of v with respect to u, right here, is just 1/2 times u to the negative 1/2. And then the derivative of u with respect to x, right here, well, we have to use what? The quotient rule for differentiation. So that would be 1 plus x times the derivative of the top minus the top times the derivative of the bottom, which is just 1, all divided by 1 plus x quantity squared. So all we do now is just replace u and v with their expressions in x. So this would be 1 plus 1 over v squared times 1/2 u to the negative 1/2, and I'm going to simplify this last factor. So this would be negative 1, that would be negative 2, right? Negative 2 in the numerator, and then 1 plus x quantity squared. Okay, extend the page. And so this would equal to 1 over 1 plus v squared times, well, let's see, the 2 and the negative, the 1/2 and the negative 2 cancel out, so that would be negative 1. And then u is what? What is u? We said u is 1 minus x over 1 plus x. So we'll have 1 minus x over 1 plus x to the negative 1/2. Okay, that would be u, and then times the negative 2 over 1 plus x squared. Okay, and so now we have to replace v with its representation in x. So v, we said, was what? V is the square root of u. So this would equal to negative 1 over 1 plus the square root of u. This would be, okay, so the square root of a function squared is its absolute value. And let's see, this would be, I'll go ahead and flip this. Since a negative exponent means to take the reciprocal. So we would have this times a negative 2 let's see, I'm sorry, that negative 2 should not be there, right? Because a half times a negative 2 is negative 1. Oops, sorry. I see a mistake here. That should be 1, sorry. Because I did the cancellation, didn't I? So that should be 1. Sorry, I almost propagated a mistake there. Okay, so I caught it in time. All right, so we'll have 1 over 1 plus x quantity squared. Okay, and then we replace u with its definition, so we'll have negative 1 over 1 plus the absolute value of u, which is, what is u? 1 minus x over 1 plus x. Like so. And we can simplify this, so this would be times 1 plus x to the 1/2 divided by, okay, that would be, excuse me, that would be, yeah, 1 minus x. Oh, sorry, not right. We have to subtract exponents, right? So that would be 1 over 1 minus x to the 1/2, okay, times, okay, so we have 2 minus 1/2, so that would be 3/2, right? 1 plus x to the 3/2, like so. Because 2 is in the denominator and 1/2 is in the numerator, okay? Let me clean that up. That should be all of this to the 1/2. Okay, and then, so 1 plus x to the 1/2 divided by 1 plus x squared is 1 plus x to the negative 3/2, as shown here. So there's the answer. All right, so this is the answer. Now, let's see here. Do we have, can we simplify even further? Square root of x squared. So let's see. Well, and then this would be square root of that. Yeah, I think we can go further. So this would be, might be kind of dangerous to go further. I think we can go with this. Yeah, we'll leave it at this. Okay, so somebody check me on this, see if that makes sense. Okay, I think there's, you can probably get some additional simplification, but this is sufficient. Okay. It's a little bit different from the solution, but I think it's okay. I'm checking. Let's see. I'm reading the what the Stuart had to say about this problem. Bear with me 1 second. Okay, yeah, so we can go with this. All right. Okay, so let's see. And how about one more problem to close out this section? How about we take the derivative with respect to theta of this function? So let's let f of theta equal to arc sine of the square root of sine theta. Okay, so we've got this. Okay, which is equal to arc sine of sine theta to the 1/2. Okay, so we want to calculate f prime of theta. So f prime of theta, so as we recall, the derivative of the arc sine function, so f prime of theta would be the derivative of the outer function. So the outer function would be arc sine function, so that would be 1 divided by the square root of what? 1 minus the function. So in this case, the function is the square root of sine theta. Okay, and then the derivative of the arc sine function is, it's 1 over 1, the square root of 1 minus x squared. In case, so we're not using x, we're using the square root of sine theta. So we have this times the derivative with respect to theta of the argument to the arc sine function, which is sine theta to the 1/2. Okay, this is the chain rule. Okay, so you see this factor right here that I've got highlighted, that is from the chain rule. All right, so now we can simplify this. So this would be 1 divided by the square root of 1 minus what? Well, the square root of something squared is its absolute value. So it would be 1 minus the absolute value of sine theta. So obviously theta can't be pi halves, right? You would have trouble. So 1 minus the absolute value of sine theta times what? Now we use the power rule for differentiation. So this would be 1/2 sine theta to the negative 1/2 times cosine theta. So there we have it. Okay, so that would be your answer. All right, so that concludes section 3.5, implicit differentiation. There's a number of interesting challenges in that section, so that will end this particular video. And so the next video we'll talk about section 3.6, derivatives of logarithmic functions.